Last time we talked about what big O analysis is, right? We used an example um, uh, comparing the runtime of moving a bunch of people using a sports car with just a one passenger seat and moving the same amount of people using a bus with an infinite number of seats, right? And um, But that's like a hypothetical example. Now let's look at some codes to make the idea more concrete, right? And here are uh, two pieces of code. So both codes actually tries to find out what's actually the minimum and maximum integer inside of an integer array. So the min int was initialized to the maximum possible value of an integer on your machine, and then the max int was initialized to the minimum possible value on your machine, and then we have a loop that goes through every integer inside of this integer array, right? Suppose this integer array has a length of n, right? What's going to be the runtime, right? So inside of this for loop, we are doing like two pieces of work, right? Two if statements. So if I is smaller than this min int, then min int is assigned the value of I, right? So, and every time you see an I that's larger than the max int, the max int was in is assigned the value of I, right? So after the loop actually finishes, the min int and max int are gonna have the minimum value, the min int is going to have the minimum value of the int array, and then max int is going to have the maximum value of the int array, right? So how do we actually uh, determine the runtime of this piece of code, right? So let's look at what's actually the smallest unit of work. The smallest unit of work is actually this if statement, and combined with this assignment, right? This assignment may or may not happen, but this if statement always happens, and this if statement also always happens, right? Um, so if you treat the if statement as one unit of work, then combined together you have 2 units of work per iteration, right? Then how many iterations you have, right? So that depends upon the size of the array. What I was saying is that the int array has a length of n, right? So you have 2 pieces of work per iteration, and then you have like n iterations because the size of the array is n, right? So it's 2 times n, right? So in principle, if you try to actually try to actually be very accurate, then you are gonna say it's O 2n, right? But don't forget, last time we mentioned one of the principles of the big O analysis. You have to drop the constant that you are multiplying with the size of the problem, right? So for this piece of code, it's actually ON, right? ON. Even though you are doing like 2 pieces of work, 2 units of work inside of the for each iteration, right? So it's ON. Now let's look at this piece of code. This piece of code actually does exactly the same thing as this piece of code, except that now I have unwrapped the loop. So inside of now we have not just we have 2 loops actually, but inside of each loop we only do like one piece of work, right? So for this for loop, we're going through the array once, and then we're trying to find what's actually the minimum value of that particular array, right? So it just does like this, like 1 unit of work, this if comparison, right? And then we're looping through the entire array again for a second time, right? And then for each iteration, we're again doing just one piece of work, right? 1 work unit. Here we are trying to find the maximum value of the array, right? So this code is actually equivalent to this code. These 2 codes are actually equivalent. You can combine them together to do like 2 pieces of work per iteration, or you can just separate the 2 lines and then do like 1 piece of work per iteration, but you have to do like 2 iterations. So what's going to be the what's gonna be the big O analysis for this piece of code, right? For this loop it's O n, right? But for this loop is O n again, right? You may want to say it's O2n, but don't forget we have to drop the constant multiplying on the size of the problem. So it's again O n, right? It's a O n runtime, right? So that's an example, right? That's an example. Now let's look at some slightly more complicated example, right? So here we have a double array, right? So the language that I'm using is actually Java. So if you have if you don't really have a previous knowledge about Java, um, you can leave your preferred language in the comments. I can actually look into that and see if I can actually construct some examples using a different language. Right? I myself know Java, know C++, and know Python. These three languages are like uh, what I'm most familiar with. I know some JavaScript and I know some Fortran and I know some yeah, that's and know some MATLAB actually. I know MATLAB quite well actually. So if you are interested in sort of looking at those examples in other languages, just leave it in the comment box. I'll try to actually construct those examples. The reason I picked Java is because Java is like the language that most people actually use. Most programmers uh, would like to. Most programmers actually knows actually. So here's a it's an object-oriented programming language. So every time you see this kind of dot notation, it means that you are retrieving a data member of that object. So double array dot length means I'm taking out the length of this double array, an array of doubles basically, right? So I is sort of the loop index that goes from 0 to the maximum index that's possible for this double array, and I plus plus just means that I'm increasing the index um, by 1 for every iteration. And then inside of this loop, what I'm trying to do is actually to 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 swap the value stored at the index I with the value that's stored at the index idx, and the index idx is actually constructed from the index I. So index idx is actually computed by using this particular formula. Basically, the length subtract I subtract 1. Every time you see subtract 1, it means it's a zero-based index. So what idx actually is it's the ith element from the end of the array, right? If you are using Python, you can just use a minus index, right? But Java doesn't support minus index. So if you want the ith index from the end of the array, you have to compute it explicitly by using this equation. You use the entire length of the array, subtract I, and then subtract 1, right? So what I'm actually doing is actually swapping the value stored in the index I with the value that's stored at the ith index from the end of the array. So basically what I'm trying to do here is actually reverse all the values that's stored inside of this double array basically. So the first element is going to become the last element of this array, and then the last element is going to become the first element of the array after the loop actually finishes. So if you look at all the operations that we're doing like 1, 2, 3, 4 operations inside of the loop, right? If you try to actually count the units of work, it becomes quite difficult because each of the operations could cost different cycles. So the exact cost of each line is could be very different, right? But it's okay. But it's okay. You can suppose you can use like the the smallest unit of work as the unit of work, right? Suppose you use this line as the unit of work, right? And then this line is gonna be like 2 times of this line, 2 times of the cost of this line, right? And then this line is gonna be like 1.3 times this line, right? And then this line is gonna be like 1.5 times this line, that kind of thing, right? It doesn't really matter which line you use as the benchmark, right? As long as you can actually, or you can just choose an abstract unit of work. Say 1 clock cycle is like a unit of work, and then all those 4 statements counts to like 300 clock cycles, that kind of thing, right? And then what's gonna be the big O analysis for this code, right? Right. So in principle, you should say if it's like 300 units of work per cycle, then in principle you should say it's O 300 n, right? Suppose the length of the double array is n, right? But don't forget that you have to drop the constant, right? So it doesn't really matter how many units of work is performed per cycle, because that constant has to be dropped anyway. So you have to drop the 300. So it becomes ON, right? So for this kind of big O analysis, once you adopt the dropped constant convention, then it becomes irrelevant how many kind of operations that you are doing inside of the loop, right? Because whatever it is, as long as the total amount of work does not depend upon the length of the array, then it's always going to be a constant, right? It's always going to be a constant times n, right? It's always going to be On, right? So what I was saying is that as long as the amount of work does not depend upon the length of the array, right? So what if the number of work or the amount of work actually does depend upon the length of the array, right? So let's look at this code, right? It's not a single loop anymore. It's actually a nested loop. So you have an outside loop. The outer loop I goes from 0 to the length of the array AR, and then inside of this outer loop, you have an inner loop with index j that goes from 0 to the length of the array, right? If you look at just the outer loop, right, then for each cycle of the outer loop, the amount of work actually depends upon the length of the array now, right? Suppose the length of the array is n, capital N, right? Capital N, right? Then for the first iteration of the outer loop, you're performing n units of work, right? And then for the second iteration of the outer loop, you're performing n units of work, right? And the outer loop iterates by n times, so you have capital N plus capital N plus capital N. The summation actually involves capital N's. And now the total amount of work is n multiplied with n. That's n squared, right? Right. So now it's not On anymore, right? Because the number that you are multiplying with the size of the problem is actually the size of the problem. It's not a constant anymore, right? So if it's a constant, you can drop it, but it's not a constant anymore because it's n multiplied with n, right? N is not a constant. N is the size of the problem, right? So now it's n squared. So for this particular piece of code, it's O n squared. The runtime complexity is O n squared, right? So now let's look at the one piece of code that I have made some very small changes here, right? So the outer loop is still the same. I goes from 0 to the length of the array, right? But the inner loop, the starting index, the beginning index has changed from 0 to I plus 1. and then still ends with the length of the array, right? And then this sort of system dot print dot out dot print ln is a Java convention for printing something to the screen, right? And then we are still doing this kind of multiplication. We're multiplying the ith element of the array with the jth element of the array, and then we are printing it to the screen, right? So what's going to be the total amount of work, right? So for the first iteration of the outer loop, how many iterations or how many units of work is going to be performed for the inner loop, right? So when I equals to 0, j goes from 1 to the end of the array. So if the length of the array is n, then for the first iteration of the outer loop, the inner loop actually involves capital N subtract 1th iterations. That's this many unit of work, right? And then for the second iteration of the outer loop, I equals to 1, j goes from 2 to the end of the array. So the total amount of work for the second iteration of the outer loop becomes n subtract 2. And then it goes on and goes on down to 1. Right? So now we have to do this summation now. Right? It's not a simple multiplication, n multiply n. Now we have to do the summation here. So what's going to be the summation? It turns out that this summation actually has a fixed value. That's n multiply n subtract 1 divided by 2. Why? Why do we have that, right? If you think about it, n subtract 1 plus 1 equals to n, right? You do the summation not in the sort of left to right order, but you add the first number with the last number. That gives you n, right? And then you add the second number with the second number from the last. That's giving you another n, right? So how many n's do we have, right? We're adding them in pairs. So how many n's we have? How many elements how many numbers we have here? The total number of numbers we have here is capital N subtract 1, right? And then we are adding them in pairs. So the total number of n's we are going to have to add together is n subtract 1 divided by 2. Right? So it's n multiplied with n subtract 1 divided by 2, because we have this many pairs. This is the number of pairs, right? And each pair sums to n, right? Maybe you are worried about what if n is an even number, or what if n is an odd number, right? It turns out that this formula actually works for both n equals to n is even or n is odd. So it doesn't really matter, right? So now we have a really complicated formula. So what's going to be the big O number for this kind of complicated formula, right? So if we actually expand it, it's going to be equal to n squared, right? Subtract n squared divided by 2, right? Subtract n divided by 2, right? So is it going to be O(n) squared, or is it going to be O(n) squared subtract n, or what exactly is going to be the big O number for this particular algorithm, right? So now let's introduce the second convention of the big O analysis. You always drop the non-dominant term. So here, what's going to be the dominant term, right? For big N, that's kind of really big. The biggest number is always n squared, right? And then this is the non-dominant term. So in big O analysis, we have to drop the non-dominant term. So this non-dominant term has to be dropped. We have to get rid of it. And now we are left with O n squared divided by 2. That's essentially 0.5 n squared. And don't forget, 0.5 is actually a constant, right? We have to drop the constant. So let's get rid of this 0.5, and we are left with O(n) squared, right? So it turns out that this algorithm is also O(n) squared, just like this algorithm, right? That's also O(n) squared.